Today, we need to discuss about the mesomeric effect. Mesomeric effect. It is just like a resonance. Basically, it is just like resonance. So, I'm gonna discuss mesomeric effect. So, mesomeric effect is of two types. The first one, which is plus M, and the second one, which is minus M. What is plus M? So plus M is basically electron donating group via resonance. I will show you what it is. And minus M is electron donating group. Sorry, not donating group. The minus M is electron withdrawing group. Via resonance. So you have seen that. If I'm gonna show you resonating structure of this, let me show you. In class 12th, if you remember, this is your phenol, and if you are going to do the write the resonating structure of this, so you know the lone pair will be moving like this. Wait a minute, it will be moving like this, and this will be moving like this. So as you can see, this lone pair, this OH is donating electron towards the benzene ring, so it will be acting as plus M. This is mesomeric effect, positive mesomeric effect. That means it is donating electron. And if you have remembered this benzaldehyde from class 12th, benzaldehyde, which withdraw electron from the ring. So that's why this CHO is acting as minus M. Is that clear, all of you?
Yes, sir.
Okay,
Yes,
so how you are going to recognize whether which one is showing plus M, which one will donate electron, and whether which one is attract electron? So always remember the one which is having singly bonded, and lone pair, so it will start donating and act as plus M, and the one which is doubly bonded and lone pair, see where the confusion is. You can see this also has lone pair, this G also has lone pair, so it should donate, so it will donate. And you can see this oxygen also has lone pair, but this will not donate, or this group is having lone pair, but this will not donate. It will start withdrawing. So always remember that the group which is having lone pair and singly bonded, that will be acting as plus M, and the group which is having lone pair but doubly bonded, it will start attracting minus M. Are you getting my point? Yes or no?
yes.
Okay. So I'm going to ask you some questions regarding this. Which one will be acting as plus M and minus M? This will be my question. So just write with me the question, or you can tell me. I will just circle it so that you will be able to tell me. You need to tell me that OCH3 is plus M or minus M. I need to draw more and more group. Then I will encircle them. You can also tell me about inductive effect as well. You should tell me inductive effect as well. With mesomeric effect, you are going to tell me inductive effect. I will encircle them after writing all this. Just wait a minute. You are going to tell me just let me encircle them. You need to tell me about this group. You need to tell me about this group. You need to tell me about this group. Whether this group, encircled group, will be acting as plus M, minus M, plus I, or minus I. Avino, are you aware of minus I and plus I?
No, sir.
It is inductive effect. Inductive effect is basically on the basis of electronegativity. The one which is more electronegative will withdraw electron from less electronegative. So the more electronegative element will be minus I and less electronegative element will be plus I. It's very simple. Okay.
Sir,
Yes,
other
sir,
than
understood.
electronegativity, how can we define which is plus I and which is minus I?
Can you repeat it again, Heather?
Yes, sir.
Are you this?
Sir, I wanted to ask, how can we define which is plus I, minus I, other than electronegativity?
Generally, you can solve on the basis of electronegativity or on the basis of hybridization. But whenever two different atoms will come, it will be solved by electronegativity difference. I told you the reason of inductive effect is due to electronegativity difference. This is the main reason. Is that clear? This this hybridization that I introduced, that also depends upon electronegativity. So it's all about the play of electronegativity. Is that clear?
Yes, sir.
Yes.
So can you repeat that double bond and single bond, what you were telling before
Okay,
this?
see, this is a group which is having lone pair. This is also a group which is having lone pair. Only the difference is this is singly bonded and this is doubly bonded. But in our mind, whenever we see lone pair, that means it will donate because it is having more electron, right? Either.
Yes, sir.
But when it is singly bonded, it will donate. But when it will be doubly bonded, it will attract. Just keep it in mind. Okay. Just like you can see oxygen here is singly bonded and lone pair, so it will donate, and that's why it is plus M. Are you getting my point?
Yes, sir. Yes, sir.
But when you are going to talk about inductive effect, you can see oxygen is more electronegative than this carbon, so it will be acting as minus I. Abhinav, are you getting my point? This inductive effect.
Yes, sir.
Okay, Abhinav, tell me about this. Whether this will be acting as minus I or plus I. What do you think?
Sir, minus I.
Minus I, because nitrogen is more electronegative than carbon. Now,
Carbon.
go for the mesomeric. You can see this is lone pair. There is lone pair and this is doubly bonded, so it will start attracting. That's why NO2 will be acting as minus M. Okay. Now see, this is lone pair and it is singly bonded, so it will start donating. So it will be acting as plus M. And nitrogen is more electronegative than carbon. That's why it will be acting as minus I. Come to this carbon. There will be no resonance. No resonance. There will be no resonance. That means no mesomeric effect. But it will be as plus I. This carbon, this is carbon, this is also carbon. But this is sp2 carbon and this is sp3 carbon. In the previous class, I told you electronegativity order of sp will be more electronegative than sp2 than sp3. Are you getting my point? Carbon with sp hybridization is more electronegative than sp2 than sp3. Now come to this point, which is very important. You can see this is singly bonded and lone pair, so it will be plus M, but it will also act as minus I or plus I. What do you think? Oxygen has negative charge, so it will act as plus I. It will donate electron. Oxygen is more electronegative, but it has negative charge, so it will donate. Is that clear?
Yes, sir.
Yes, sir.
Can I change the slide? Now see, this is lone pair and singly bonded, so plus M. And chlorine is more electronegative than this, so minus I. And you can see there is no mesomeric effect. And minus I. Chlorine is more electronegative than that. So it's very simple, I think, right?
Sir, in bigger compounds, how will we be able to distinguish this?
Bigger compound like what? Heather, what do you think about bigger compound? What does it mean?
So for example, chlorine is attached to the benzene ring here. For example, if a bigger compound, like much bigger than chlorine, is attached to the benzene ring, then how will we distinguish if it is
No,
a
no,
minus
no, no,
or
no.
plus?
Much bigger than chlorine. That means you are going to tell me like this. This is your benzene, and with benzene, some group is added like this.
Yes, sir, kind of.
Kind of. You can write your bigger compound and take a picture of this and send it to me in chat box. It will be more beneficial.
Okay, sir.
Basically, this resonance depends upon the conjugation. Where there will be conjugation, there will be resonance. Okay. So you can send it to me. Okay. The one most important, everyone knows how to write the resonating structure, yes or no? Please do reply.
Yes, sir.
This is your OH phenol. You are going to write the resonating structure of all this. Abhinav, if you don't know, just let me know how to write the resonating structure. I will explain it.
Sir, I know.
Okay, very good. Then draw the resonating structure of phenol and then go for the resonating structure of benzaldehyde. And everyone knows that what is nucleophile and electrophile, right?
Yes, sir.
Okay. Iram, are you able to write it? Alia, are you there? Yes, sir. Can you write the resonating structure of this? Okay, please do. Okay. Okay, I'm gonna show you, just match it. This will move to this side and this will move to this side. And you can see there will be negative charge, and then there will be double bond between oxygen and air, and there will be positive charge like this. Again, this will move to this and this will move to this. So as you can see, negative charge moves to here, double bond here, and there is double bond and then OH positive. Again, this will move to this and this will move to this. Now, as you can see, there is negative charge, there is double bond, and then there is double bond and OH positive. Now, like this, and you can see double bond moves to here, here, and this will be like this. Now, my question is now here. If an electrophile is here, everyone is done with the first resonating structure of this, the resonating structure of phenol. Yes or no? Iram, Heather, Avino,
Yes, sir.
Alia. Now see, if an electrophile comes in this 3 structure, where this electrophile, on which positions it can attack? Electrophile, that means it is having deficiency of electrons. So it will attack either at ortho, this negative charge, either it will attack on this para, and either it will attack on this ortho. That means whenever a plus M group comes, this plus M is ortho and para directing. As you can see, due to this plus M, negative charge comes on the benzene ring at the place of ortho and para. That's why this plus M are called ortho para directing. Electrophile will directly attack on negative charge because that is electron rich site, and negative electron rich site is at ortho and para. Is that clear, everyone? Please do respond.
Yes, sir.
Avino and Heather.
Yes, sir.
Okay, now see. Just wait a minute. Very good. Now see. This will move to this. So this will move to this side. So I'm gonna show you. This will be doubly bonded C, and this will be singly bonded O negative, and H is there, and there will be positive charge. Now you can see this will move to this side. So the positive charge will be at para with respect to CHO, and the double bond moves to here, and there was a double bond, and then there is a double bond, and then O negative H. Now come to this point, this will move to this side. So the positive charge at ortho, you can see positive charge is here, double bond, double bond, double bond C, and O negative and H is there. Now again, if you are going to move this, you are going to move this, and you will be getting this. So double bond, wait a minute, double bond will be at this, and this, and then C double bond O. Now if any electrophile comes, where it will attack? Electrophile, that means electron deficiency. And you can see if it wants to attack at ortho, there is positive charge. It is already having deficiency of electron. If it wants to attack at para, there is already having deficiency of electron. Again, there is having deficiency of electron. So it will attack only at one position, that is meta. At least it doesn't have any negative charge. At least it doesn't have any negative charge, and that's why this is basically minus M, since it is electron withdrawing from the ring. So minus M is meta directing. Minus M is meta directing. For this electrophilic substitution reaction, minus M meta directing, and plus M ortho and para directing. Is that clear, everyone? Can I change the slide?
Yes, sir.
Okay. Now, whatever I have written, I'm going to write it here. All plus M group for benzene ring, obviously, benzene ring is activating, plus M is activating. That means electron density increases in the benzene ring group and increases in the benzene, and activating for what position? Ortho and para directing, we can say. All plus M is activating and it is ortho and para directing, and all minus M, you can see all minus M group for benzene ring, you can see these are deactivating. These are deactivating. Deactivating, that means it decreases electron density. Electron density decreases, and hence it is directly meta directing. Meta directing. So this will be very, very useful in the chemical reaction of all the chapters. So please be careful. Can you change the slide? Isam, Heather, Avino, can I change the slide?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now see, I'm going to start a new topic, that is aromatic, non-aromatic. This is very important. And then comes pure and anti-aromatic and anti-aromatic. Now, rules to decide whether which one is aromatic and which one is anti-aromatic or non-aromatic. First one, compound should be cyclic. Compound should be cyclic. The second one, compound should be planar. Compound should be planar. What does this planar means? Planar means each atom of ring should be sp or sp2 hybridized. sp or sp2 hybridized. The third one we can write, compound should have complete conjugation. Complete conjugation in ring. Complete conjugation in ring. And the fourth we can go for on Huckel rule. We will talk about Huckel rule. First, I'm going to explain this 4 points. 3 points. See, to be aromatic, the compound should be cyclic. And compound should be planar. Planar, that means carbon in that should be sp2 hybridized, or the atom, each atom should be sp2 hybridized. Now compound should have complete conjugation. That means in the ring, there is all the carbon or all the atoms should have participate in resonance. And then comes to the Huckel rule. Huckel rule we will discuss. Before that, keep it in mind, if any one of the 4 rules fail, if any one of them fails, then it is non-aromatic. Then it is non-aromatic. If any one of the 4 will fail, then it is non-aromatic. Is that clear? You don't need to check other conditions. Now see, what is Huckel rule? Huckel rule is very important. And what is Huckel rule? So I'm going to explain. So 4n plus 2 pi electron, 4n plus 2 pi electron, this is, and 4n pi electron. 4n plus 2 pi electron, that means n is equal to 0, that means 2 pi electron. N is equal to 1, that means 6 pi electron, and n is equal to 3, that means n is equal to 2, that means 10 pi electron, and so on. And if you are going to put this n is equal to 1, it will be 4 pi electron, 4 pi electron, and n is equal to 2, that means 8 pi electron, and n is equal to 3, that means 12 pi electron. Now see, if all these three is followed or these conditions are satisfied, compound is cyclic, compound is planar, compound is having complete conjugation, then if you are getting either 2 pi electron, 6 pi electron, 10 pi electron, 14 pi electron, 18 pi electron, 22 pi electron, then it is aromatic. Then it is aromatic. And if this three is fulfilled and you are getting the pi electron as the multiple of 4, then it is anti-aromatic. Then it is anti-aromatic. Let's take an example to get it better with. You can see if you have a benzene ring, first you are going to check whether it is cyclic or not. So it is cyclic. First, it is cyclic, so it is satisfied. Now whether it is planar or not, so you can see each corner atom or vertex atom is carbon, and each carbon is sp2 hybridized because it is making double bond, so it is planar. So it is planar. So I'm going to write planar it is. Now if you are going for complete conjugation, you can see complete conjugation is there. You can check it like this, or either you can check it like wait a minute, whether you can check it like pi sigma pi, sigma pi, sigma pi. Complete conjugation is there, that means conjugation is there. Then you are going for pi electron. Pi electron, you know, in one bond 2 electron is there, and there is 3 pi bond, 3 pi bond, that means 3 to 6 pi electron, and 6 pi electron comes here, that means benzene is aromatic. Is that clear? And if you are going for an anti-aromatic compound, you can see, first of all, you need to check whether it is cyclic or not. Yes, it is cyclic. Now go for planarity. You can see 4 carbon is there and each carbon is sp2 hybridized. So it is planar. Now go for conjugation. You can see pi, sigma, again pi, sigma. So it is what we say, complete conjugation. Complete conjugation is there. Now go for the pi electron. You can see 2 pi bond is there, that means 4 pi electron, so it is anti-aromatic. So this is how we decide. Is that clear? Can you change the slide?
Yes, sir.
Okay, you need to tell me whether which one is aromatic, anti-aromatic, and non-aromatic. One, two, three, four, five, six, seven, 8, Please do let me know. Alia, will you be able to solve it? Okay, please do it.
Sir, first is non-aromatic.
Very good. First is
Mistake.
non-aromatic. Very good. Because it is not cyclic, it is non-aromatic.
Sir, second one has only 2 pi electrons, right? So I'm not sure if it's
No,
anti-aromatic.
see what you need to do. First, you need to check whether it is cyclic. Yes, it is cyclic. Then planarity. See, this is your sp2 hybridized, which is planar, which is also planar. But this carbon is singly bonded sp3. So it is not planar. And since one of the rule is failed, so it is again non-aromatic.
Okay, sir.
The third is also non-aromatic.
No, it is aromatic. I'll show you.
Sir, but the
See.
OH carbon is the sp3 hybridized.
No, it is not sp3 hybridized. This carbon is making 4 bond, and in which one is pi. We just count for hybridization.
Yes,
We
sir.
count lone pair plus sigma bond, right, Heather?
Yes, sir. Yes, sir. Yes.
And sigma bond is 3 only, and lone pair is 0. So
Got it, sir.
sp2 that is. Okay, please do the rest.
The fourth one is aromatic.
Very good.
Fifth one is anti-aromatic.
Fifth one is,
I mean, aromatic.
it will be aromatic because cyclic, yes. Planar, yes. Each carbon is sp2 hybridization. Conjugation, yes. Pi sigma vacant orbital. Pi sigma vacant orbital. Then 2 pi electron is there. That means it is aromatic. Go for the sixth one.
So the aromatic.
What you just say? Aromatic.
No, aromatic.
See, this is your cyclic. Yes, cyclic. Planar. Yes, planar. Because this is your sp2. This is also your sp2. This is also your sp2, and this is also sp2. Go for the conjugation. Yes, conjugation is there. Pi sigma vacant orbital. Vacant orbital sigma pi. So conjugation is there. Now count the pi electron. So 1 and 2. 2 pi bond is there. 4 pi electron. So it is anti-aromatic. Alia, it is anti-aromatic, right? 4 pi electron.
Sir, can you explain this 4 pi electron rule once again?
In sixth one, for the sixth one.
No, sir. Overall, like the pi bond rule, the pi electron rule.
Pi electron is what? See, if I'm asking you simple
Sir, I know the
question.
pi electrons, but like you told us four conditions, right?
Yeah.
Aromatic or non-aromatic. The fourth condition in which was the number of pi electrons. I didn't understand that fourth condition.
Okay. Okay. Fourth condition is very simple. You have Huckel rule. I'm gonna write it again. Huckel rule, in which if you will get 4n plus 2 pi electron, all the three satisfied, and if you will get this, then it is aromatic. I will explain it again. And if you are getting all the three and then 4n pi electron, then it is anti-aromatic. How you will get it? You can see, if you are going to put n is equal to 0, you will be getting 2 pi electron. If you are going to put n is equal to 1, you will be getting 6 pi electron. Are you getting my point? At the place of n, you are going to put 1. 1 into 4, 4 plus 2. If you are going to put 2, you will be getting 10 pi electron. If you are going to put 3, 14 pi electron, and so on. If you are going to put 4, then it will be 18. If you are going to put 5, then it will be 22. And if you are going to put here n is equal to 0, you are not going to put here because it will be 0 pi electron, but which is not possible. N is equal to 1, 4 pi electron. N is equal to 2, 8 pi electron. N is equal to 3, 12 pi electron. And n is equal to 4, 16 pi electron. Are you get, and how you will calculate pi electron? So it's simple. Pi bond is there. Double of the pi bond will be equal to pi electron. Is that clear, Heather?
Yes, sir. And we have to find out the n.
No, we don't need to find out the n. You need to count the number of pi bond and then calculate the pi electron and then match it. 2, 6, 10, 14. There will be difference of 4. Next 18 pi electron. Next 22 pi electron. Actually, we only deal up to this or this. We cannot go above this. We will not go because it will be a very large compound. Are you getting my point? How I am matching it? You can see in all this pi electron is very less. Here the pi electron is 6 pi electron. If you are going to check this, you will get 6 pi electron. You are going to check it, this is 2 pi electron. If you are going to check it, this is 4 pi electron. And you know 4 pi electron, it is multiple or table of 4, so it is anti-aromatic.
Okay, sir.
Please do the rest.
Seventh is aromatic.
7th is aromatic, right?
Yes, sir. Eighth is non-aromatic.
8th is non-aromatic. Is there any other answer for the 8th one?
So it is anti-aromatic, no? Just to-
8th is anti-aromatic. See what will happen. First of all, this pi, what is this? This is in conjugation. You can see this is your pi bond, sigma, and lone pair. So it can be pi bond. That means this is your pi electron. So 2 pi electron you will get from here. And this is also in conjugation. So 2 pi electron from here you will get. and this is your pi bond. That means 2 pi electron here. From here you will get, and total 6 pi electron is there. And since an electron is becoming pi bond, so you will not count this in hybridization. So this is your sp2 and this is also your sp2. See how you are going to recognize whether this lone pair or the negative charge is pi electron or sigma electron. Simple. If it is in conjugation, like this is your pi electron. If it is not in conjugation, then it is not pi electron. So it is aromatic.
So
Like
can
this you can.
explain the seventh one then?
Yeah, Iram.
The seventh one, can you explain it?
The seventh one, you didn't solve it. Okay. See,
No, I didn't
the
understand.
seventh one is like this, right? You can see cyclic it is. Then go for hybridization sp2, 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 sp2. That means planar it is. Then go for conjugation. You can see pi sigma vacant orbital, pi sigma vacant orbital. Yes or no?
Yes, sir.
So what do you think? And 2 pi electron is there. So it is aromatic. Okay.
Okay, sir, I understand.
What about the ninth one? Let me draw ninth one again. What do you think about ninth one? This one. Any answer? Okay, let's see.
It's
Is
aromatic.
it cyclic? Yeah, very good. Cyclic. Count this. First of all, you need to see this pi sigma lone pair. That means this compound is delocalized. Delocalized, that means delocalized, that means it is pi electron. It is pi electron. So what you need to do, see, this is cyclic and this is also planar. This is also planar. sp2 hybridized conjugation, yes, complete conjugation is there, and 2 pi electron, so 6 pi electron, it is aromatic. Okay. Done. Now see, the next topic is basically your hyperconjugation, which is also very important. Hyperconjugation, which is also known as no bond resonance, no bond resonance, which has also other name, that is Baker-Nathan effect. Baker-Nathan effect. Now see, First of all, what is this hyperconjugation? You saw that inductive effect is only partial displacement of electron. Partial displacement of sigma electron. Resonance is complete delocalization of pi electron or pi bond. And hyperconjugation is complete transfer of sigma bond electron or sigma bond electron, and only applicable for cation, free radical, alkene, alkyne, and phenyl. Only applicable for this, not carbon anion system. Next, at least one alpha hydrogen is required with respect to carbocation, free radical, double bond, triple bond, or phenyl. This is what we see. Basically, you can easily tell me, or you can easily know how many hyperconjugative structure is in the compound. For resonating structure, we generally draw the resonating structure, then we come to know. But here we can easily look at the compound and easily tells us that which one, how many hyperconjugative structure is there. Now see how we are going to check it. It's very simple. If you have an alkene, or if you have a carbocation, or if you have a free radical, or if you have a triple bond, or if you have an alkene like this. Okay, wait a minute. Now you can see. I'm gonna show you. It's very simple. Now you can see here. With respect to this alkene, we have 3 carbon, and with respect to this system alkene, whichever carbon is connected, that carbon is known as alpha carbon. The carbon which is directly connected is known as alpha carbon. Now you can see, and the hydrogen which is connected to, this alpha carbon is known as alpha hydrogen. So you just need to calculate alpha hydrogen, and you know each alpha carbon will have 3 alpha hydrogen. So we have total 9 alpha hydrogen. If you want to calculate alpha hydrogen with respect to this, you can see 2 alpha carbon is there, this and this. This will have 2 alpha hydrogen, this will have 3 alpha hydrogen. So this will be here 5 alpha hydrogen. With respect to this, again 5 alpha hydrogen. With respect to this, you can see 3 alpha hydrogen with this alpha carbon, 3 alpha hydrogen with this alpha carbon, 6 alpha hydrogen. With respect to this system, this is your 1 carbon which is having 3 hydrogen. That means 3 alpha hydrogen. So you need to know how we calculate number of alpha hydrogen and number of hyperconjugative structure. We can write directly. Please do write this. I'm gonna write a point about this, which is
Your voice is breaking.
wait a minute. Stability directly proportional to number Heather, did you say anything?
Yes, sir. Your voice was breaking a lot.
Okay. Am I audible now? What I was saying, I'm going to repeat it. Sorry. So, are you able to understand this? How we calculate?
Sir, could you
How we
explain?
calculate? Yes, yes. Iram, am I audible now? Just let me know
Yes,
if am I audible or not.
you're audible, sir.
Now see, have you understood how we calculated number of alpha hydrogen? Yes or no?
That time is. I didn't understand the bond.
Yeah. Okay, okay, no problem. If you were, if I was not audible, that is not a big deal. I will explain it again. See, this is your alkene. I am taking every example, each type of example. You can see this is your ketone, cation. This is your radical, free radical, and this is your alkyne, and this is what I'm gonna take is your benzene. Okay. Now I'm gonna explain. Focus here. With respect to this, you can see this is your an alkene. So the carbon which is directly connected to alkene is known as alpha carbon. So there are two alpha carbon here, right? Yes or no? The carbon which is directly connected to alkene is alpha carbon. And how many alpha hydrogen is on alpha carbon? 3. So these 3 hydrogen is known as alpha hydrogen, and this alpha carbon is also having 3 alpha hydrogen. That's why it will be total 6 alpha hydrogen. Are you getting my point?
Yes,
Yes,
sir.
sir.
Now you can see with respect to this system, cation, this is your alpha carbon, this is your alpha carbon. This will have 2 hydrogen and this will have 3 hydrogen. So this will be 5 alpha hydrogen. Now with respect to this, again 5 alpha hydrogen. With respect to this, again 6 alpha hydrogen. With respect to this system, we have 3 alpha hydrogen. Did have you understood how we calculated alpha hydrogen? You can see this carbon is alpha carbon and it has 3 hydrogen. So the number of hydrogen which is attached with alpha carbon is known as alpha hydrogen. Yes or no?
Yes, sir.
Now
Understood.
see, very good. Now what you need to do, a stability directly proportional to number of alpha hydrogen, number of alpha hydrogen. Okay. If I will give you 3 compounds, you just need to calculate the number of alpha hydrogen with respect to either whatever is given. Like alkene it is, carbocation, free radical, alkyne or phenyl. And also remember that number of hyperconjugative structure will be equal to number of alpha hydrogen. Whatever is the number of alpha hydrogen, that will be equal to the number of hyperconjugative structure. Okay. Now I'm going to give you a question.
Sir, how did we identify the alpha carbons?
How did you?
How did we identify the alpha carbons?
Alpha carbon is very simple. The carbon which is directly connected to this radical, this is your alpha carbon, this is your alpha carbon. This is not, because it is not directly connected. This is alpha carbon. The carbon which is directly connected to the system. System means either alkene directly connected, carbocation, free radical, alkyne or phenyl. Is that clear?
Yes, sir. Yes, sir.
And what is alpha hydrogen? The hydrogen which is connected to the alpha carbon. So I'm gonna give you a question, and the question is, this is your A. Then I'm gonna give you another question. This is your B. Then I'm gonna give you this. This is your C. Tell me how many, which one is more stable? You need to arrange them.
Sir, C is the most stable.
Just wait a minute. I'll verify. Okay, Iram, sorry. Were you saying anything?
Sir, I said was C the most stable.
Yeah,
Yes, sir.
very good. So see, this is your system. So 3 alpha hydrogen with this is the system, 6 alpha hydrogen with this, and this is the system with this 9 alpha hydrogen is we have. And there is 0 alpha hydrogen because with this system, there is no carbon that is connected. If no alpha carbon, that means no alpha hydrogen. So C will be the most stable, then comes your B, then comes your A, and then comes your D. Is that clear?
Yes, sir.
So I'm going to give you some question on this. Let's move. So first of all, I'm going to write here application of hyperconjugation. Hyperconjugation. First of all, you need to take care of this stability. We give preference to first resonance, then hyperconjugation, then we will go for inductive. And also stability with respect to hyperconjugation is directly proportional to number of alpha hydrogen. Now you are going to do this. Arrange them in increasing or decreasing order of stability. Please do this. Are you done with this?
Sir, A is the most stable.
Wait a minute. I'm just going to give it ABC forward to write it. Which one will be the most stable?
A.
A. How many alpha hydrogen does he have? 9 alpha hydrogen.
Yes, sir.
What about this? How many alpha hydrogen does B have?
8.
8. How can you say that? This is your system. And only the carbon that is directly connected is this,
True.
right? So only one alpha hydrogen, because one hydrogen will be there only. Yes, or no, Heather, Iram,
Yes, sir. Yes.
Alia, and Avino, you are not participating or not responding. Avino, are you not getting this? What about this one? How many alpha hydrogen? You can say this is your system. This is the 2 carbon which is directly connected. So 5 alpha hydrogen. If you want to arrange this A, C, and then B. So my internet. Okay, no problem. Okay, the next question I'm gonna give you this one, and then this one. Please do let me know which one is more stable, A or B.
Sir,
You
Sir,
have
I'll have to leave class because I need to go break my fast. Is that okay?
okay. Heather, what about you? I mean, which one is more stable? Alia?
Sir, we'll consider both the systems here, right?
System is not benzene, this is alkene. So you can see with respect to this, you have this and this. That means 3 plus 2, 5 alpha hydrogen, and with respect to this 2. That means total 7 alpha hydrogen. Okay. And with respect to this, if you are going to take 3 alpha hydrogen from 2 alpha hydrogen, total 5 alpha hydrogen, and with respect to this, you will be getting 2 alpha hydrogen from here, and you already counted this. So total 7 alpha hydrogen. But if you are looking at the first diagram carefully, then you will be able to realize pi, sigma, pi. That means resonance is also there. So in A, resonance plus alpha hydrogen, and this is only alpha hydrogen. So A will be more stable.
Okay, sir.
Can I change the slide?
Yes.
Okay. Now I'm going to give you some a very good question. Now the third question. This is your A. This is your B. And this is your C. The fourth question. This is your A. And this is your B. The fifth question. Let it be. Please do this.
So C, B, A will be the order for the third question.
Yes, this will be your answer. Because if you are going for alpha hydrogen, how many alpha hydrogen in the first one?
2.
2 or 1?
1.
1 alpha hydrogen. What about the second one?
4.
How many? 4 alpha hydrogen. Very good. What about the third one?
5.
So the answer will be CBA, right? Everyone? But this is wrong. But this is wrong, and this is very important. A stability order will be, I'm going to tell you, a stability order will be B, then comes your C, then comes your A. This is the 1 alpha hydrogen. Only we need to find between 4 alpha hydrogen and 5 alpha hydrogen. Why it is so? Because the angle strain will be more here. The angle strain will be more here, because you can see this is your sp2 and this is also your sp2, which is 120 degree, and this is your sp3. So it will be 109 degree. So angle strain will be more here. That's why it is less stable in spite of 5 alpha hydrogen, B will be more stable than C, and then at last A will. Okay, please do write it. It's important. Alia, the compound in which angle strength is more. Basically, angle strength comes when we are going to talk about the cyclic structure. So when you are going to see this is your sp2 hybridized and this is your sp2 hybridized, and sp2 hybridized has a carbon which is 120 degree, and this two angle is 120 degree. Basically, two carbon is sp2 hybridized and one carbon is sp3 hybridized. sp3 has 109 degree approximately. And in this, if you are going to look at this compound, this is your sp3, this is your sp3, and one angle is sp2. So you can see two angle which is 109 degree, lesser angle strength, and here you can see it is 120 degree, sp2 2 carbon, which is greater angle strength. If angle strength, if you want to, if some compound is like this, and if you want to make it more, the angle strength will be there. If the angle strength more, then the stability is less. So angle strength here is more and more. That's why B is more stable than C. Is that clear, Alia? What about this last one?
But A will be more stable.
Why A will be more stable? First of all, let me know the number of alpha hydrogen. Abhinav, you can reply in chat box, Abhinav. What is the alpha hydrogen, number of alpha hydrogen? Alia and Avino. Heather, what is the alpha hydrogen? No, not two.
X.
6 alpha hydrogen, because you can see, Avino, we are talking about alpha hydrogen, not alpha carbon. So this is alpha carbon and this is also alpha carbon, which is connected with 3 hydrogen. So 6 alpha hydrogen. And if you are going to look at this, there will be 6 alpha hydrogen because of 2 alpha carbon is here and alpha carbon is here. Now, which one is more stable? As you can see, if I'm gonna write this, there is CH3 and there is CH3, which will basically repel each other. Bulky group on the same side, that will repel each other. And you can see, if bulky group is on opposite side, this is your cis and this is your trans. So bulky group, opposite side, B will be more stable than A. Trans is more stable than cis. Okay. Can I change this? Can I change this line? Now we are going for the last topic, and that is acidic strength. For acidic strength, you have to know that acidic strength directly proportional to minus I. The group which is more power to attract or withdraw electron, or we can write minus N. The group which will attract pi electron towards it or withdraw pi electron, or we can write Ka. Ka is acid dissociation constant. Acid dissociation constant. Or we can write inversely proportional to pK, which is inverse of K, that's why inversely proportional. Or inversely proportional to plus I, or inversely proportional to plus. This is very simple. If it is directly proportional to withdrawing group, it will be inversely proportional to donating group. Okay. So I'm going to give you some question and you are going to solvent. Can I change the slide? You are going to arrange this. Compare acidic strength. First, I'm going to give you a phenol and I'm going to give you an alcohol. Please do.
So B is more acidic.
No. ROH is more acidic. How can you say that?
Sorry. It is
You
basic.
just, oh, wait a minute. I forgot to write OH here. Sorry, it's my mistake. And you are right. In that case, B will be more stable. Sorry, B will be more acidic, I think. Now, please do this.
You can explain this one.
Which one is more acidic?
B.
B. No, it's wrong. You have studied this in class 12. You can see phenol, always remember this. Phenol more acidic than alcohol. More acidic than alcohol. Now see. Since it is an acid, it will give H plus, right? It will give H plus. Yes or no?
Yes, sir.
And this is also acid, so it will also give H plus. Do you know this negative will be in resonance and that's why it will be stable, right? Yes or no? Please tell me. Heather, we know.
Yes, sir.
Now you can see that O is negative, that means electron rich. And I told you in the inductive effect that R is alkyl group, which has plus IF. It is already having a lot of electrons and it is donating electron more and more. It has tendency to donate electron and it doesn't want any electron. So it will destabilize, yes or no? Yes or no? Heather, Alia.
Yes, sir.
So that's why you can see this phenol will easily donate H plus and will go to form an anion because in this it is also stable and this is not stable, so it won't go easily and hence phenol is more acidic than alcohol. Okay, is that clear? Can I change the slide? Okay, I'm gonna give you a question, simple question. The last question. In next class, we are going to start aromatic compound. Please do this.
D will be most acidic.
What you just said?
Sir, D will be most acidic.
Yes, D will be more acidic because it has P group which is attracting or withdrawing. Then comes your C, then comes your B, then comes your A. Is that clear, everyone?
Yes, sir.
In the next class, we are going to cover aromatic hydrocarbon, which is a very small chapter. And after this, in the next class, in the same class, we are going to start alkyl halides. So I will recommend you to please do the basics of this chapter. At least the preparation